in the future, a lot of people will look back and think of Hubble and think of Cassini and think of Voyager and the lunar landings as a real golden period of exploration. Long may it last.
This is Bob Berman, and we are looking at the live lunar eclipse presented by SLOOH and Google. SLOOH is SLOOH. You're probably watching this on eclipse.slooh.com, but certainly slooh.com will take you to other wonders of the world if you wish. And I'd like to introduce our next guest. She's a solar expert, and since we're in a plugging mood right now, I'm going to unashamedly say that my book, The Sun's Heartbeat, published by Little Brown, will be out in a month. And it's only because of writing this book that I can probably not come across as a complete idiot while I interview our next guest, Lucy Green. Now, the sun is, of course, the nearest star, and it is sunlight that we're still seeing on the moon, even though the moon is fully eclipsed. So let me welcome Lucy Green from England. Are you there?
I am here. Hi.
Hi.
Hello, Lucy.
Hi.
So what do you think so far? What do you think of this eclipse?
Oh, it's been fabulous so far. And actually, I'm looking out of the window in the UK, and it's kind of clearing up. So I'm hoping to catch the tail end or be able to see it out of my window later on.
Hooray!
It's been fabulous to see it through SLOOH.
And could you tell us something about, you told me on the phone the other day about how, I was wondering how we were going to tie your sun expertise in with a lunar eclipse, and you pointed out that the moon's surface is changing because of being hit by sunlight. That's true, isn't it?
Yeah, that's right. So the moon is being bombarded by sunlight, but also by particles coming from the sun. So I'm a solar scientist, and I viewed the sun probably differently to a lot of people. Certainly before I started studying the sun, I viewed it as this separate object in the solar system that was quite unconnected to us here on the Earth. But now, after having studied it, I see the sun as an object that gives off lots of particles, something that we call the solar wind. And these are charged particles, and they flow out from the sun all the time, and it's a gusty wind. And it flows out to the edge of the solar system, 17 billion kilometers away.
Yeah, so I understand they ridiculed Eugene Parker in the 1950s when he first came up with that idea. Astronomers were saying, "What a stupid idea that is! A wind that blows from the sun." Yeah, right.
Yeah, that's right. And now it's such a fundamental thing for us, and it creates beautiful things like the comet's tails. It's the reason that cometary tails blow off and create these millions of kilometers long, beautiful effects. But the interesting thing...
So they're like comet tails are like weather vanes, aren't they? That are being blown by the wind from the sun.
Yeah, that's right. And actually, one of the PhD students that I work with, is interested in using comet tails to investigate the wind being blown off from the sun. And he's wanting to work with amateur astronomers who are taking photos of the comets and then put all these images together and kind of get a map of how the solar wind, how these particles from the sun, how it varies across the solar system, which is just such a fantastic
how
idea.
Interesting. Yeah, it's great.
Fascinating. You know, they say the best way to learn about anything is to write a book about it. So I found in this last year and a half just fascinating things I never knew about the sun. I'm just sorry that I didn't contact you, because you said something the other day to me that was fascinating. We know that for over a century now that the solar phenomena are essentially magnetically induced. But didn't you say something that these giant storms on the sun, these CMEs, are places where how did you put it? Where it's necessary for the sun's health, right?
Yeah, that's right. I study the magnetic fields of the sun's atmosphere. So these particles that blow off in the form of the wind, if I can describe it that way, ultimately come from the sun's atmosphere. But there's also these very large magnetic fields there, and they too erupt into the solar system and form something called a coronal mass ejection. And for people that know me, I'm always talking about coronal mass ejections. But they are necessary for the sun. The sun creates a magnetic field deep inside the star, and it rises into the sun's atmosphere. And if it doesn't get ejected, then it would endlessly accumulate. So I see these coronal mass ejections as a valve for the magnetic field to escape the sun and prevent an endless accumulation. But, the magnetic field goes somewhere. And I was really intrigued by the NASA news story last week, I think it was, about the discovery by the Voyager spacecraft, which are now at the edge of the bubble of hot gases and magnetic field created by the sun, the edge of the heliosphere that it's called, and how it's all bubbly at the edge of where these Voyager spacecraft are now. And I just thought, that was just fantastic, because that's where these bubbles of magnetic field in the form of coronal mass ejections end up, right at the edge of the solar system.
What a time to be alive, huh? What a time to be alive.
Oh, it's fantastic.
Now, are you involved at all in helioseismology?
I'm not, but I pay a lot of attention to it, because helioseismology is the only way in which we can study the interior of the sun.
Could you tell our listeners and viewers what that is?
Yeah, so it's a really nice technique that uses the fact that the sun rings like a bell, because it has sound waves bouncing around inside the star. And these sound waves, they're emotion, sound is emotion, and it causes the surface of the sun to move up and down. And we can actually measure these movements, which is incredible. So you look at the surface of the sun rising up and down and all the patterns that are created, and then you take those patterns and you can infer what's happening inside the sun. It's very mathematical, but incredible. They do it for the sun, but they also do it for other stars too. But
so is it a little bit the way earthquake experts here, seismologists, can infer what's below the Earth's surface because of the motions of our surface? So the same thing is done with the sun. Would you say that's accurate?
Yeah, absolutely, yeah. And we'd like to do it on the moon as well, actually. So a technique that can be used throughout the universe.
Oh, you brought up a good point, because didn't we find that the moon, when it's struck, rings like a bell for up to 2 hours?
Yeah. The moon has sound waves in it, and it's thought to have quakes, moon quakes. So it's one thing that before we maybe put humans on the moon, if we're ever able to do that might need to be studied. You might want to make sure you build your lunar base somewhere that's free from moonquakes. Yeah. So,
Now, a number of people are saying, I've noticed there's a difference here between Duncan, who optimistically was saying that we'll return to the moon someday, I'm sure we will, and Lucy, who's a little more, I would say, realistic perhaps, or maybe pessimistic, saying that if we ever do go back to the moon. But one of the stoppers is something that Lucy mentioned earlier, and that is those particles from the sun and radiation, which one of our women astronauts, Shannon Lucid, who spent more time in space than any other U.S. female astronaut anyway, really believes will be a stopper, that the amount of radiation. I've read a figure that on a 2-year Mars mission, the astronauts will get so much radiation that somewhere between 15 and 40% of their brains will be destroyed.
It is something that has to be considered, yeah.
Yeah, and even us smart people can't afford that.
Absolutely, no. I think I'd be out of a job if that happened to me. But
I'd be in an awful state.
These particles that come from the sun, they're very small. They carry a charge, and they have a lot of energy, and they're constantly blowing out from the sun. But there are also other events, similar to the coronal mass ejections that I mentioned earlier, but other events called solar flares. So between the solar wind, coronal mass ejection, and solar flares, you get a lot of very, very high energy particles given into the solar system. And on the Earth, we're protected by the fact that we have a magnetic field. That's a really good barrier to these particles. But the moon is moving in and out of the Earth's magnetic field. And so I kind of see the solar system with magnetic eyes. So the sun has a magnetic field, the Earth has a magnetic field, and the moon is skimming in and out of the Earth's magnetic field. So sometimes on the lunar surface you're protected from that coming from the sun, but then when you move outside of it, you're not protected. And so the Apollo astronauts in particular, I think actually it turns out they were quite lucky to not have received big particle doses from the sun. They managed to not be on the lunar surface when some large solar flares happen.
Yeah, I understand that Apollo 17, if it had happened a month or so later, it would have been a different story.
Yeah,
Yes.
I read that they think that fatal doses of particles would have been received by the astronauts. These are small, high-energy particles that can penetrate the skin and give you radiation sickness. I mean, that could be a headache, or it could be low blood count, but it could be cancer. It could be fatal.
I think some of them actually experience the particles that you're talking about, Lucy. I remember interviewing. This was for another program some time ago now. It was Charlie Duke again, an Apollo 16 astronaut, and he was talking about there was an experiment that was conducted while they were on the way to the moon. It was a very strange occurrence.
With the flashes?
Exactly, the scintillation inside the eyeballs, the flashes. And I got to look. There was a chap who was a researcher in Houston who I also interviewed, and he showed me very high-powered scanning electron microscope images, of very, very high-powered images of the helmets of the astronauts. And what was shocking is you could actually see where these very high-energy particles had burrowed through the helmets, and of course they would have ended up passing through the brain. And the astronauts were seeing these flashes.
I'm told that in the earlier flights, the early Apollos, the astronauts were seeing these things. And to our viewers and listeners, they would have appeared like streaking meteors suddenly across the field of view, and the astronauts reported seeing them about once a minute. At first they didn't say anything because, being old-time test pilots, I can tell you as a pilot myself, I'm not a test pilot, just a small airplane owner, that you never report anything that's wrong with you to any aviation physician.
Exactly.
You just know never to do that. So they didn't, but some of them were talking to each other, and they realized they were all seeing it, and Mission Control knew that, that these were mostly protons, high-speed protons from the sun, and what could they say? Everybody knows this isn't good for you.
Yeah, it's interesting, isn't it? I think even inside I said that the Earth has this magnetic field and that it blocks the particles from the sun. And I kind of was truthful when I said that, because it blocks most of the particles coming from the sun, but some do make their way in, and then they get trapped in the Earth's magnetic field. And the particles then that are trapped also have high energy, and there are various processes that act on these particles and can increase their energy. So even once you're inside the Earth's magnetic field, you still feel the effects of high-energy particles. So even astronauts on the International Space Station will probably see the same effects as the Apollo astronauts, and are still at risk of cell damage because of these particles.
Is that what gives rise to the aurora, Lucy? The northern lights, the sort of shimmering lights we see in the sky at night, if we're in northern latitudes and southern latitudes. Is that the same sort of process?
Yeah, it's exactly the same thing. And they're the most beautiful manifestation of the fact that we have all these charged particles coming from the sun into the Earth's magnetic field, and then being energized, and then they are able to, we don't fully understand the processes, but they can spiral down the Earth's magnetic field lines and hit the Earth's atmosphere. So
we're looking forward to that. We get them up here in upstate New York fairly often. I think it should be mentioned that a swarm of particles from the sun has its own magnetic field, and only if its field is opposite to ours. Of course, Earth has a field with north up, so only if the field is opposite will it transfer its energy to us. Otherwise, it'll be channeled harmlessly away from us. But the ACE instruments, the ACE spacecraft, located almost 1 million miles sunward of us, is the first place that can actually measure the magnetic polarity of the incoming particles. And so this doesn't give us a lot of warning, which is why you often hear that an aurora may happen if there's a CME or other great event on the sun, but half the time it doesn't, because the magnetic polarity has to be correct. And I also understand from I spent 3 years up in Alaska as a aurora lecturer.